needs to do. So as a counterexample of that, on the interactive voice response server project, we had a fairly compact set of tools that cost a whole lot less than $500,000. We had a QA partner, which is now called Silk, and that's what we use to drive the call center applications via the graphical user interface call center application. And then we had custom-built load generators that would interact with the interactive voice response servers, sending DTMFs and listening to DTMF tones coming back and understanding, okay, this is where I am in the call flow and so forth. Middleware, we had custom-built middleware to allow us to do end-to-end testing from the IVR side through to the call center side and vice versa. And we used a lot of free tools like the TCL programming/scripting language, if you will, to create test components. So here's the architecture of the system under test. You see over on this side we have basically the call center. So we've got customer service agent and content management agent and another customer service agent. And then we have, this is the excuse me, the back end, if you will, the that should include this too, of the call center. It does call routing and so forth. And then out here we have the interactive voice response servers. So to test that, we've got QA partner, and it's set up to allow us to kind of interact with these guys here through their GUI. And we've got our load generators that are able to drive load in through here. And it's not just driving load, it really is interacting. I mean, it's the ability to tell when something has happened so they can figure out what's gone on and make intelligent decisions. And then what we can do is the load generator, which really actually is a test tool, not just generator of load, it actually is able to do intelligent testing, is able to drive stuff all the way through to a particular desktop. So it can make things happen. Now, if you do make something happen, you need to be able to go over there and say, hey, did that thing I want happen? And that's where the middleware came in, because the middleware would allow us to reach around back here and go, yep, we saw it on the screen, a little yellow dot, or nope, no yellow dot. So you see there's a real mix of the commercial and the open source and the custom built here. Okay, last lesson. Don't believe it when people say, oh, performance testing, wait until when functional testing is done and system test, then you can start performance testing. That is going to be too late. Performance, load, and reliability problems are often design problems ultimately, and if you've got a design problem, you don't want to wait until months potentially later to fish the thing out of there. It's you want that design problem identified and removed fairly early. So don't just say, oh yeah, stabilize the functionality here and then everything will be fine and we'll run the performance test. That's a classic example of the testing worst practice of testing on the assumption that everything is going to pass. And you want to test on the assumption that you're going to find bugs. And in the case of performance, load, and reliability bugs, those are going to be serious bugs. So we should try to look for them early. So design reviews, modeling, as I mentioned before, unit testing, looking for bottlenecks in the units, component integration testing, making sure that subsystems don't create bottlenecks between them and their interfaces. Because once you get into a situation where you've got really slow, brittle, unreliable system, and it's in system test, if you're thinking that you're going to be able to patch that by throwing hardware at it and so forth, that's really not something that's going to necessarily work. And I'll show you an example of that not working here. So on the interactive voice response server project that I mentioned, where the IVR server eventually proved to not be a very scalable beast, there was actually a senior technical staff member who had built a spreadsheet model that predicted a lot of the problems that later showed up. It was amazing how prescient that model was, and if you think, oh well, those models can't be really accurate, I mean, he actually predicted the number of simultaneous users that would bring the system to its knees to within something like plus or minus 10%, and so that was pretty amazing. The problem was that this guy had built this thing, but there was no follow-up. Nobody actually took that and said, hey, this is a warning shot. This is the canary in the coal mine, as the saying goes, and we really need to deal with it. And it didn't happen. And so once we got into system test and later component integration test and system test, and started finding the problems that I mentioned, like the system crapping out and dying after just beyond 50% load, what happened was there was an attempt to try to throw hardware at it. And so if you think, I mentioned that phrase hockey stick before, and I'll show you what that means. If you graph response time against level of load, and what you'll typically see in a system that's functioning well is a nice kind of gradual, more or less linear increase in the response time as the load goes up. But once you get out to the limits of supported load, which is shown by the vertical bar here, then you're still within the allowed response time, which is the horizontal bar over here. But when you get into a problem, what you see is a couple things. One is you might see the slope of the line clearly indicates that you're going to go shooting out of the allowed response time well before you hit the load. But then you get to the other thing. You get to this hockey stick or nonlinearity. Basically, what's happening here is some form of saturation. Some resource is saturating, and that's bottleneck. And then, yeah, you can address that. So this first resource saturation that happened on this project was CPU. So bang in on our CPU board, and away we go. Yeah, okay. And then so here we are with the additional CPU board, and that's fine. Let's see if I can do this properly here. That's maybe on track to actually be somewhere within the range. Probably more like here, a little bit outside, but then wicked nonlinearity kicks in again, and whoosh, there's the hockey stick thing happening. We're rocketing up there, and then so that turns out to be we've got a throughput issue on the I/O channel. Oh yeah, we'll add some more capacity to the I/O channel. Okay, well, all right, here clearly on track to be okay, except again, boom, what's it this time? Memory. There's going to come a point where you try to peel the onion. If you start off so far away from where you need to be, as you saw we were over here, that you just